In this lecture, we're going to be talking about the boost converter. So as the name implies, a boost converter steps the voltage up. So the output voltage would have a greater magnitude than the input voltage. And so I've gone ahead and drawn the circuit for a boost converter here on the left. As you can see, just like in the buck converter, we have one inductor, one capacitor, the output load, and then one diode and one transistor. And so similar as well to the buck converter analysis that we did, we're going to say that we're going to switch transistor Q1 on from 0 to pi, and we're going to switch it off from pi to 2 pi. So the control signal for transistor Q1 would look like this. It would be on from 0 to pi, then 0 from pi to 2 pi. And also remember that the duty ratio for the converter is the time during which the transistor is on. So this time right here from 0 to pi would be equal to D times T. In other words, the duty ratio times the period. And then the period would be from 0 to 2 pi. So this would be T. So if we say that the transistor Q1 is on from 0 to pi and then one period is 2 pi, then that would be the same thing as saying that the duty ratio is 0.5. In other words, transistor Q1 is on for half of the time. And so let's go ahead and do the same thing that we did for the buck converter. Basically, we're going to see what the circuit looks like from 0 to pi when transistor Q1 is on, and then we're going to see what it looks like when it is off. So let's go ahead and write this down. From 0 to pi, we have state 1. And so during that, like we said, transistor Q1 is on. So the circuit would be like this. We have Vn through L1 through Q1, and then back to Vn. And also remember that the voltage across inductor L1 would be VL1. And then we're going to call the voltage across diode D1 VAK1. And so remember that we've said that for the boost converter, the output voltage is going to be greater than the input voltage. So we know that the voltage right here at this point, which would be the same as the output voltage, is going to be greater than the voltage at this point right here, right? Because the voltage on the anode of diode D1 would be Vn minus VL1, whatever that drop is across L1. And we know that Vn is lower than Vout. So that means that VAK1, or the voltage from anode to cathode on diode D1, has to be negative because Vout is greater than Vn. So we know that for this state, we're switching Q1 on. So let's go ahead and write that down. Q1 is on. And we know that the voltage from anode to cathode on diode D1 is negative. So that diode needs to be off. So we're going to say that diode D1 is off. And so if we write down the voltage loop equation around the equivalent circuit that I've drawn here on yellow on the left, we would get that minus Vn plus VL1 is going to be equal to 0. So then when we get that VL1 is going to be equal to Vn during state 1. Now during state 2, we're switching Q1 off. And so the energy that's stored in inductor L1 needs to flow somewhere. And so it's going to flow through the freewheeling diode D1. In other words, the energy that's stored in inductor L1 when Q1 goes off is going to be forced through D1. It's going to force it on. So we know that the circuit during state 2 would look like this. We're going to have Vn through L1, through D1, through the output load, and then back to Vn. So let's go ahead and write it down. State 2, we're going to have Q1 is off and D1 is on. So let's see what the voltage loop equation would look like. We would have minus Vn plus VL1, and then D1 is a short circuit, and so we have plus Vout is equal to 0. So we would get that the voltage across inductor L1 would be equal to Vn minus Vout. And again, all I did here is I solved for the voltage across inductor L1 during the two states using Kirchhoff's voltage law. So basically the voltage around any loop needs to be 0. And so remember that we said in the buck converter analysis that the energy that's stored during state 1 on inductor L1 needs to be equal to the energy that's discharged from inductor L1 during state 2. In other words, the energy that's stored in inductor L1 over one period needs to be 0. So whatever is being put into it is being taken out from it during one period such that the average comes out to 0. And so that's very important because that means that the converter is operating in steady state. If that wasn't true, then we couldn't say that the converter is operating in steady state, because that would mean that every cycle we would be either discharging more than what we're putting into L1, or we would be putting more energy into L1 than we're taking out from it. So either the energy would be going down every cycle or it would be going up every cycle. And so that by definition is not steady state. So now knowing that, we can calculate what the output voltage to input voltage relationship is going to be. So let's go ahead and write that down. We're going to say that dt times Vn plus 1 minus d times t times Vn minus Vout is going to be 0. And so I did the same thing for the buck converter, but I actually skipped one step. This should technically be over L, and this right here would be over L as well. So this term on the left is the term for the energy that's stored in inductor L1 during state 1, and then the term on the right, so this term right here, is the energy that's discharged from L1 during state 2. And so the reason why I didn't include L in the buck converter analysis is because that cancels out. So it's not really that important for calculating the relationship between the output voltage and the input voltage. So now if we distribute out the terms, and I'm also going to cancel out T from here and here. So this equation would become D times Vn plus 1 times the term on the right, Vn minus Vout, so plus Vn minus Vout, and then distributing the D, so minus D Vn minus minus plus D Vout is going to be 0. So we can see here that dVn is going to cancel out with minus dVn. And then let's factor out V out here. So we would get Vn plus V out. And we have D minus 1 is going to be equal to 0. So this is the same thing as saying Vn is going to be equal to V out times 1 minus D. So I'm moving V out to the other side of the equation and multiplying times minus 1. So then we would get that the relationship between the output voltage and the input voltage, V out over Vn, is going to be equal to 1 over 1 minus D. Or in other words, V out is going to be equal to Vn over 1 minus D. So this right here is the relationship between the output voltage and the input voltage for a boost converter. And so remember that D goes from 0 to 1. And really more practical applications, that would be more like 0.1 to 0.9 for the reasons that I mentioned in the buck converter analysis. So, but let's say for example, if D is close to 1, then we would get 1 minus something close to 1, so almost 0. So Vn over that number is going to be a large number. Or if D is 0, then we would get Vn over 1, so Vout would be close to Vn. So let's do a few examples. Let's say that if D would be equal to 0.1, then we would get that Vout would be equal to Vn over 0.9, which would be equal to 1.11 Vn. And let's say what happens if D is, instead of 0.1, is 0.9. So we would get that Vout would be equal to Vn over 1 minus 0.9 would be 0.1. So this would be equal to 10 Vn. So I just took two numbers just to kind of illustrate how the boost converter steps the voltage up. So by varying D from 0 to 1, we can get a higher voltage at the output than the input voltage.